It looked like you had something. All right. Also not quite later. So has everybody turned in their synthesis plans? All right. I'll take a look at those. You might get your exams emailed to you today. Maybe. And you might not. If you don't, it will be Wednesday before I get them to you. I've got office hours for the week posted. I'll be outside here after class, and I'll stick around. You know, I'll either stick around for an hour or until everybody's. I'm sorry about that. If you're watching at home. And I will get some problems up today. Yeah. It was electronic. Okay. Pass it up to me. So take a picture of it before you pass it up to me. If you brought it, how many of you brought it like a hard copy? Brought it with you. If you did that, go ahead and not right. I mean, you did submit it online. How many of you didn't submit it online and brought a hard copy? Take a picture of it if you would, and then pass it up to me so you have the file. We'll see. It's not going to be that big a deal how it gets done. And like I said, that 14 points will just go straight onto your exam score. Then the assignment due on Wednesday. Remember, there's another one due on Wednesday. For that one, the idea of putting those online is you can submit them online. I can grade them in Canvas. Those are just 10 bonus points. All right. That is correct. I will only take PDF. We're in it correctly. Like, make sure I can read it. Because you guys are like, oh, well, it's not that big a deal. But if I have to reorient 40 of them, I will be really annoyed by the end of it. So any more bonus points or accommodations, like every time I have to accommodate like file types, which is not a big deal. Like that goes down. The odds of me doing another would go down. Okay, so last time we finished with the directed aldol. Take this back up. Go ahead and figure out what the product of that will be. We'll talk about that down the road, though. do the chemistry right now. Right, give you another minute or so on this. All right, so first thing you got to do first, what is LDA? It's a really strong base, the non-nucleophilic really strong base. I drew it last time, I'll draw it again, just so we know what we're talking about. There's a lithium there. That lithium isn't it. So I get asked this a lot. Like there are a lot of details we don't go into, experimental details, ratio. Well, I'll show here in a minute, right? The product we're going to get out of this will give you you'll have diastereomers. So the ratio of the diastereomers, that depends a little bit on the cation. It depends a little bit on solvent, which I haven't put here. Right. That's all stuff that you will worry about if you take an intermediate organic or advanced organic, or if you become an organic chemist, you'll have to worry about those details. Usually you can change those though, right? Like you can control what solvent is used because you're the one that has to go and pour the solvent into the flask. You can usually choose your cation. You can certainly add other cations to mix in there with it. So you want to get the fundamental reaction down first. And that's going to be an acid-base reaction. LDA is almost exclusively going to be used as a really strong base. These isopropyl groups, right? So the basic atom is the nitrogen. It's surrounded by these really bulky groups. So it has a hard time being a nucleophile. It's hindered in being a base. But again, protons always sit on the outside of the molecule. They're the most accessible part of a molecule. This I've given you, a ketone that only has 2 protons that could be deprotonated, right? The 2 in the alpha position to the carbonyl. The alpha position on the other side of the carbonyl has 3 methyl groups on it. There are no protons there, so you can't make an enolate on that side. So the reaction is going to be proton transfer from the ketone to the nitrogen. Draw these out. I'm going to draw it as the carbanion, and then you're going to end up with the neutral amine. The lithium the counterion there goes with the enolate. So you guys, there's a pKa table on the Canvas page. If you didn't see my announcement, you might find that useful for the assignment on Wednesday. The one I left out, you kind of have to consider the different kinds of nitrogens, right? So there's that NH. There's that NH. Those two NHs are different. Right, so the pKa table I gave you has this one. And this one's going to be a pKa of like, I don't know, somewhere in the 30s, 33, 34, 35, something like that. The pKa of a proton on a quaternary nitrogen, a nitrogen that's got a positive charge, this pKa is going to be like 9 or 10. Right? Obviously, very, very different things. And so we make this one. We have this really strong base. If the conjugate acid of a strong base is going to be a weak acid, right? So this thing is a weak acid. So it's not going to be a protonated nitrogen. Well, a quaternary nitrogen. It's going to be a neutral NH. All right. So that should be the enolate that you got. Then, so this is the product of step 1. And I still saw a lot of people on the exam not noticing 1, 2, and 3, or as you design your synthesis. Like we talked about the synthesis, there were a lot of mistakes on the synthesis, but this one shouldn't have happened, right? If you're writing a whole bunch of reagents down, you can't write sulfuric acid and hydroxide. Like it might be 1 sulfuric acid, 2 hydroxide, and then a whole bunch of things like that, right? 1, 2, and 3 means we do this first, then this, then that. If I don't have these numbers there, it just means I mix LDA, this ketone, and acid, which doesn't make any sense. So you have to write the 1, 2, and 3 in. All right, and I really recommend as you go through these, like figure out what the product of step 1 is, write it down, write step 1 beside it. Not necessarily in your answer to me, just like as you're working the problem. So then we're going to put in step 2. 1, 2, 3, 4, 5. All right, so step 2 is this. Again, we haven't added step 3 yet, so this is still under basic conditions, right? We add a strong base, we're going to get an enolate. The enolate is also a strong base. So a nucleophile now, and it will add into the carbonyl. You're going to get that. That's basically what you're going to get every time. You're going to have a carbonyl, the alpha carbon that is negative, the former carbonyl carbon bonded to an O-. And then you have to bring along the 2 things bonded to this carbonyl in the first place. So there's going to be an isopropyl on it. And I left something out. The enolate carbon, the carbon that was negative, is bonded to a methyl. Got to be a methyl there. So if you number this, these numbers, if you're not numbering for nomenclature, you can just on the first molecule put any numbers you want anywhere, and then just make sure that numbering system stays constant, right? So in this reaction, carbon 2, there's an arrow from carbon 2 to carbon 4. That makes the 2,4 bond. There's no arrow from 1 and 2 or 2 and 3, so 1 has to stay bonded to 2, 3 has to stay bonded to 2. There's no arrow from 4. I guess we can name these, number these others. 5, 6. So 4 and 6 stay bonded, 5 and 4 stay bonded. So this is the product of step 2. And also at this point, I said I would talk about this. That product at that point can exist as diastereomers. It can exist as two chiral diastereomers. We can have the methyl and the oxygen both out. We can have one back, one out. All right, and then each of those are chiral, so there's an enantiomer. So you get 4 stereoisomers out of that. We have 2 chiral centers. 2 chiral centers, 2 to the 2 is 4. We get 4 stereoisomers. Step 3 then is just going to be to protonate. So that would be your product. Questions about that reaction?
Well, we did get like you have dominated plus and
So yeah, if you want to do eliminate it, yeah, so you could.
but that's not included in those first 3 steps.
Right. H plus workup is just you're protonating things that need to be protonated. Yeah. So yeah, if you had heat here, or you had heat here, your final product is going to look something like. Right, you're doing elimination, and the double bond is going to end up conjugated with the carbonate. So like I said, solvent, I can't remember, I don't think, the book might get into it. You can affect the diastereomeric ratio, like how much of the final product has both OH and methyl pointed the same direction, how much has them opposite. You can change that ratio. It's very hard to get that ratio to be 100 to 0, but you can change that ratio by changing the cation, by changing the solvent, by changing, well, you can change the base. You could use some other super strong base. What's the other thing you could do? Yeah. Oh, sorry, the temperature. You can make the reaction colder. You can make the reaction warm. And you can change that diastereomeric ratio.
Is that what changes dehydration?
Yeah. Okay. What you can't change, this whole reaction, whatever product you get over here is going to end up racemic. Like, obviously, this is not a chiral product, but this one would be. Both diastereomers would be chiral. They're going to be racemic unless there's something in there that is optically active. Right now, all we have, LDA is achiral, the ketone is achiral, this ketone's achiral. So everything's achiral, it's going to end up racemic. All right. Predict the product of that reaction. Then ask yourself if it would be different than the bottom reaction. Keep your head down if you want to keep working on the products. You have the products, you can look at those. Well, if you have the products, or if you're not sure of the products, look at those and see if you can explain the difference. Why they're two different products. Temperature. It is not just the temperature. It's a little bit. Temperature plays a role.
You have IPA, that's such a strong base that it only contains, that you only get it. That's insane.
So there's no equilibrium. All right, so yeah, the difference is that LDA is a way stronger base than hydroxide. All right, so in both cases, like if I had just given these to you and said, what happened here? Right, on the top, you obviously make the enolate here, right? So that carbon, you don't have to know what else happened, but that carbon has to become an anion. That's the nucleophilic carbon. On the bottom, that carbon is the nucleophilic carbon. Right, so that's the difference. And the reason is, if you look at this, so the temperature is different. There's two things change. We obviously can't do a reaction in water at minus 78. Minus 78, water is a solid. But that's not really the difference, but it kind of does get to it. So, I should have drawn this a little lower. So let's think about so here are the two enolates. This is the first time I've given you guys a molecule that can make two different enolates, right? There are two alpha carbons pretty much on any ketone. Well, on a ketone, there are two alpha carbons. If both alpha carbons have a proton, you might be able to make two different enolates. In fact, you can sometimes make up to 4 different enolates, right? So if you have 2 di-substituted alpha carbons, you can get E and Z isomers and the enolate. So what I want you to do now is draw the resonance structure of these two enolates. I've drawn them with the carbon minus. I want you to draw them with the O minus. And then ask yourself, which one do you think is more stable? All right, so I've drawn the two enolates with the negative charge on the oxygen. Draw an enolate this way, the carbon-carbon bond is a double bond, right? So we've got an alkene here, we got an alkene here. And so the way you end up judging the stability of enolates is by the stability of the alkene. You treat it just like an alkene. All right, from Orgo 1, you saw this in Orgo 1, whether you remember it or not. The tetrasubstituted alkene is more stable than the disubstituted alkene. A conjugated alkene is more stable than a non-conjugated alkene. That doesn't come in here, but you should keep it in mind. Okay, so ask yourself about these reactions. Hydroxide pulls off the alpha proton, again, enolate and water. Right, so water, move this over here. Water is the conjugate acid in both of these. Water has a pKa of 15.7. pKa of a ketone is going to be about 19. So what's true about this is hydroxide does pull that proton off, but the reaction goes backwards really easily. In fact, backwards is favored. All right, so both of these reactions go backwards. And what that means is you wind up getting an equilibrium mixture. All right, so you're going to have most of the enolate be the more stable enolate. That is, this is the thermodynamic enolate. What do you think that means about the enolate on the bottom? You get the kinetic enolate. Why is that the kinetic enolate? And when I say that, I mean this would be the enolate on the right. Why is that one the kinetic enolate?
It's less sterically inert and
What?
The two methyl groups are electron dead.
They are, but it's series. Yeah, so because in the end, if that really affected it, you're going to judge this. Yeah. So the methyl is more accessible. Remember over here when I was talking about LDA, I was talking about that nitrogen being really sterically hindered. Right. So if I need a nail, I don't know where this is coming from. If I need a nail and I've got like a big bucket of nails, or I've got a little box that's like sealed and I have to open it, I'm going to pull out of the big bucket until I run out of them. Even if the nails in the sealed up thing are fed, they're cold or something. Right? So that's a terrible analogy. Forget I said that. It's a lot easier to get into this methyl group. If I want to take a proton there, well, one thing, there's three of them. Just statistically, I just reach for a nail. If there's 3 times as many of one kind of nail as the other, I'm probably going to grab the one that is 3 to 1. But it's also easier for me to hit this, right? So if I mix a whole bunch of nails up, right, the ones with the really big heads on them, and I have 3 times as many of those as the tiny little nails that you can just put all the way through something, and I put all the tiny ones on the bottom and all the big headed ones on the top, I'm obviously going to grab from the top first. Right, so this proton is sterically more accessible. The big bulky base comes in, takes that proton. That actually happens with hydroxide as well. Even though hydroxide is not very sterically hindered, the two methyls do present steric hindrance. The hydroxide will primarily grab the methyl proton first. You get to here. But usually what happens at that point is the reaction just goes backwards, right? Any one individual molecule of this ketone is going to bounce over here, come back, bounce up here, come back, bounce over there. And at equilibrium, since this is more stable, there's going to be more of this. All right, again, it's equilibrium. So you're never going to get to a point in this particular case. The difference in stability is not so much that you're going to have 100% of this. So you're going to have like 95% of this, 5% of that, and that gets reflected in the mixture of your product. On the bottom reaction, LDA, right? Let's do this. So LDA makes this enolate. LDA is a big bulky base. It reaches in, it grabs the proton off the methyl. And that's it. It's stuck there. Right? Even though it could get to a more stable place, right? pKa at 33 here, pKa at 19 up there, that's a 14 order of magnitude difference. The back reaction is not going to happen a whole lot. So even though this is not the most stable enolate we can form, it forms the fastest. And this is, by and large, going to be 100%. If that was an ethyl instead of a methyl, it wouldn't be 100%, right? Like if I had an ethyl here, there's going to be one methyl group. It might not be 100, it would be like 98 to 2 or something. All right, so same thing as we did back with the dienes. We're gonna get the thermodynamic enolate when the deprotonation is reversible. And we're gonna get the kinetic enolate when it's not. And you're going to judge that since how strong a base the enolate is sort of set. Like an enolate is going to be a really strong base. An enolate's always going to be a stronger base than hydroxide or methoxide or something like that. So really what tells us that we're going to get a thermodynamic enolate or a kinetic enolate is the base we use to make the enolate. If we use a really strong base like LDA, we're going to get the kinetic enolate. If we use a strong base, but not as strong a base like hydroxide, we're going to get the thermodynamic enolate. I keep emphasizing this. I don't know how much it sinks in. I do want you guys to think of hydroxide as a strong base. All right. The reason I want you to think about that, and the reason humans call hydroxide a strong base, is that to us, to the chemicals that make up our body, hydroxide is a strong base. Right? I don't want people leaving this class thinking, oh, I can just like drain them. Right? So for your body, hydroxide is a strong base, but there's a lot of molecules for which hydroxide is not a very strong base. These ketones are those. LDA is a strong base, basically no matter who you are or what you are. Right? If you spill LDA on yourself, it will quickly turn all the water it encounters into hydroxide. And it will do its thing. Like you're still going to get the hydroxide effect, but it won't be noticeably worse. All right, so this is obviously only going to come up if you have two different enolizable protons. Right, so it's only going to happen for ketones. And it's only going to happen for ketones that have two different groups on them, each of them having at least one. So it's a pretty specialized thing. Like over here, if we had tried to use this ketone as the electrophile, nucleophile, right? This would be the kinetic enolate product. We would deprotonate there. LDA would get there. But again, the difference in sterics between this position and that position aren't terribly great. We did not use this. We did not use this as a nucleophile. We used it as an electrophile. There's no proton transfer. Questions about that? Now's a good time for a break. Go outside and run around. So you might have noticed that I wrote this little thing over here. Sorry if you're on the recording. It's really important information. I'm gonna project the exam 3 date for November 30th. What else is November 30th in your lives? Lab final. Good. My students are on top of things. Anybody taking Bio 160? Yeah, all right. I'm working with some of my colleagues to try to get another exam added in there for some of you. Wait, that's not what I was supposed to do. So here's what my plan is right now. It looks like we are going to have to come, for those of you in my lab, we are going to have to come downtown to do some lab stuff. We're going to have to, I don't know what we're doing yet, but I've been told you can't tell your students not to come downtown. So for those of you in bio, at least some of you have contacted me and told me you're in bio right before this class, which means you run for a bus. So I'm going to offer a version. We're going to start over here. That group, if you get down here late, I'm going to start you late, basically. So I'm going to give you a little bit. I'll write this down. You don't have to follow it. If you're not in my lab and you don't have a Bio 160 exam before my class, there's at least some that are on Wednesday. Whatever. I've been told by multiple people that there's a bio exam. So I'm trying to this will not affect most of them. It's a handful, but I don't want people having to run from a bio exam, catch a bus, get up here, take an exam, 10 minutes later, give an exam over there. All right. So hang with me, everybody. If you don't have a class before this and you're not in my lab, just come take the exam like you normally would. Wednesday, November 30th, that is also our last day of class. I don't really like giving an exam on the last day of class. It's better than the Monday to me after Thanksgiving. And it's better, we could have it the Monday before we go, but the amount of material on the exam will not change. So you're talking about 10 less days to study. Okay, good. So Wednesday, look, what day do you want to take the exam? In your heart of hearts, when do you want to take the exam? You don't want to take the exam, right? I know this. You do not want to take the exam. So if you're not in a class before this one, and you're not in my lab, come take the exam normal time. If you are in an exam before this one, I'm going to offer a 40-minute later start time. It's going to be one later start time. We'll work out what it is. It'll start next door. Then for my lab exam, we're actually going to do whatever crap they make us do for, sorry, Brian. We're going to do whatever crap we have to do in the lab to clear out a lab. And then maybe we'll all have a cup of coffee and then we'll take the exam, right? So there'll be some downtime that you can breathe. Is that bad? Cool. Yeah, if you're not in the lab, you don't get a vote. All right. Thanksgiving is so this will be 6 days after Thanksgiving. All right, so like I said, there's really not another date we can do exam 3. And we are doing exam 3. I am not yet that far gone in my career that I won't give it. Likewise, I'll say this right now, the final, I believe, is scheduled for 2 p.m. December 7th. That's a month. I love it when I do that. When I tell you guys when the final is, you guys are just oh, it's 1 month from today, we'll be taking a final exam. I will offer, hang with me, I'm trying not to totally disrupt the class. I will offer one other exam time for the final. One. All right, I'm not going to give the exam all week. I also have a life. Doesn't really seem like it, but I do. All right. Last thing, where are my Phillies fans? What the hell? All right. There's more enolate chemistry. We're not even close to done. That's not actually true. We probably will start a main chemistry on Wednesday. So if you're one of those who likes to look ahead in the chapter before you come to class, you might look over chapter 22. Any questions about enolate stuff I've done up to now? All right. What is the name of this compound? You'll recognize this compound from exams such as 2. Okay, everybody who said ethyl first, good start. You name, well, what's the functional group? It's an ester. So carbonyl, carbonyl oxygen, alkyl. Esters start with the alkyl. All right, so this is ethyl. You're going to make this from ethanol and what acid? Acetic acid, right? So acetic acid would be this. So this is acetate, ethyl acetate. You guys have used ethyl acetate in the lab. Any of you who ever take paint off of fingernails or other parts of your body will also have used ethyl acetate. Maybe toluene. Look that up for me. Or you can not no, like I mean on the bottle. If you actually use huh? Great. You can buy ethyl acetate at hardware stores. Good compound. Smells a little like glue. What is going to happen here? What acidic or basic? How do we know? That K is a potassium positive. That means not O is negative. That's potassium hydroxide. That one I'm not gonna. Yeah, I should probably make you guys know those. But so hydroxide is OH minus. O methyl minus is methoxide. O ethyl minus is ethoxide. That's the base. Potassium methoxide is the base. Ethanol is not a base. Ethanol is a very weak base. Ethanol is a very weak acid. But in most of these reactions, and I did see this a number of times on the exam, right? So acidic or basic conditions, and most of you identified that correctly. But then, so like the middle one on the exam, sulfuric acid and ethanol. You're like, okay, we're going to protonate things. And then you use the ethanol to be the proton token. Okay, ethanol is a much weaker acid than sulfuric acid. So again, anytime you've got to do something with a base, whatever the strongest base in the mixture is, that's what's going to do it. Right, so when my wife and I are in my kitchen and we got to get something off the top shelf, she does not get it off the top shelf. I do. She sure could have added that to the store. Likewise, right? If we got to get something that she's crammed way back in some low down your drawer, she gets that because again, she's shorter than me. Right? So potassium methoxide, ethanol. If something's going to happen with a base, it's going to be with the ethoxide, not the ethanol. Right? If I use ethanol as a base, I make ETOH2 plus. That's a strong acid. I can't make a strong acid under basic conditions. All right. So ethoxide can do two things. One thing it can do is just be a nucleophile. Right? It can add into the carbonyl. What happens if that happens? Let's draw that. Actually, draw what happens if ethoxide adds into the carbonyl. Just the first step, draw the addition of ethoxide into the carbonyl. I just figured out what's bugging me about the clock. All right, so. That's what you get, right? Ethoxide adds into the carbonyl. It's that tetrahedral intermediate. Is that tetrahedral intermediate chiral? No, it's got two ethoxies on it. So what happens next? Exactly right. The only thing that can happen at this point, right? With an O minus to kick out one of the ethoxy groups. That just takes us back to the starting material. That absolutely happens in solution. Right? Just doesn't do anything. This is also the reason anytime we're gonna end up making an enolate, right? So the only other thing that can happen, you can deprotonate here on the alpha carbon. Make an enolate. Anytime you want to make an enolate with an ester and an OR base, the ORs have to match up. Because if you imagine I started with a methyl ester, but I used ethoxide, at this point, right, I started with methyl ester, I have this. And now it's not 50-50, this is chiral. And when I kick OR minus out, I can kick methoxide or ethoxide out. And what I'm going to get in the end is just a mixture. Right? I'll have some methyl ester, I'll have some methyl ester. So you always want these to match. All right, so that's not going to be productive. Let's make the enolate instead. Knowing what you know about enolates, predict what happens next. Just the very next step. You don't have to go all the way through it if you don't want. But if you want to, you can. All right, remember, you've got, so the very next thing that could happen, you just go backwards, right? This enolates, sorry, this proton over here, the alpha proton has a pK of about 23, 24 on an ester. Ethanol has a pK of about 17, so this is not favored. But in analogy to the aldol, enolate can attack the ester. And that's also reversible. So all these are reversible. What happens from that? Yeah. So again, anytime we add nucleophiles to carboxylic acid derivatives, this is chapter 20. Nucleophile adds in, the X group, whatever it is, can get kicked back out. Chloride, OR, SR. So here, this O minus can kick out oxide. It's also reversible. There's actually one last thing that can happen. So there's going to be an acid-base reaction at the end of this. So I'm not drawing all the agents in, I'm drawing all the different kinds of agents in. One of those 4 protons is going to get deprotonated. Which one? Why would it be that one? So, right, I mean, no, that's perfectly good logic. This whole thing, all these things, everything we did on Wednesday last week, I always want to say Friday when I do that. Everything we did last week, everything we've done today, right? The proton on the alpha carbon is acidic because of the carbonyl. Right, that carbonyl's electron withdrawing. I just, 10 days ago, if I draw this reaction, you guys would have told me I was nuts. So you probably wouldn't have considered it like class. But you would have thought this guy's lost it, right? Everybody's been yelling at me all for a year and a half, like you can't pull protons off carbons. And then we do, right? So the reason that CH is acidic is because of the carbonyl. Well, if one carbonyl can make an H acidic, 2 carbonyls will be better. More is always better, right? So let's draw that. So ethoxide is going to take that middle proton, draw the anion you get, and then draw resonance structures. All right, you're still going. So, yeah, so the CH here between the 2 carbonyls, that carbon, the one I've got my pinky on right now, is alpha to 2 carbonyls. right? It's impossible for us to have an oxygen with an H and between two carbonyls, right? Because oxygen gets two bonds. So if this was an oxygen, there could not be a proton. That can be a nitrogen, and those compounds are really acidic. So a nitrogen that sits, an NH that sits between two carbonyls is quite acidic. So is a CH. There are two protons here. I'm not showing them both, but there are two protons on this carbon. Both carbonyls are pulling electron density away from that H, weakening that CH bond, polarizing it. Base is going to go on the proton, deposit the electrons. This is the carbanion you would get. Right, and then that negative charge can delocalize up into the right carbonyl, and you get this thing. And now you've got a double bond that's conjugated to the carbonyl, the one carbonyl, and you have an O minus. So you put the charge on the more electronegative atom. Or you can move that the two electrons, the lone pair, the other way. Again, you get a double bond conjugated to a ketone and an O minus. So if these two structures are both resonance structures of the same structure, this is like grade school commutative property or whatever, right? These are resonance structures of each other. We've delocalized that negative charge over 5 atoms, 2 of which are oxygens. That's better than 3 atoms, 1 of which is oxygen. And so the pKa for this one, again, it's like 8 to 11 or so. Like it's a reasonable acid. You can completely deprotonate that proton with hydroxide. You can mostly deprotonate it with an amine. So now that proton is acidic, like on a human physiological scale. The other thing, we'll come back and talk more about this in a minute. The other thing is, this is essentially irreversible. This thing's going to have a pKa of like 9. And sorry. We get ethanol over here is the other thing. Ethanol has a pKa of 17 or so. This one, I think this one actually has a pKa of 9. This particular molecule, again, know the ranges. We don't have to know exact numbers. Anyway, it's like 7 or 8 orders of magnitude. So this reaction, to get this product, all of these are reversible, right? Every step up to the last one is completely reversible. And in fact, on the first step, equilibrium lies to the starting material. So to make this reaction go all the way through, we have to be able to deprotonate here. There's going to be a book problem on that. I'm sure there's a book problem on this, where like if we got to this point and there were 2 methyls here, the reaction doesn't go. We just end up back at the start. That's a level of, we'll get there. Right now, I just want you to take that down. You can actually start. We'll do another example of that. Based on that, draw the product for the reaction I just put up. Sorry. If you wanted that as the product, you would end up getting this actually is the final product after you would prove it. So if we want this, once we add protons, we get it. Right. But the only way to get there is to do the deprotonation. So which proton is going to be there's two possible products in them. Which proton can be, which proton, this is the wrong base, the wrong damn base. There's a bunch of, this is the product. Yeah, no, I wrote LDA there, good. I gave you guys the wrong base.
That's a weak one.
It's a weak base. So the problem with it, I tried to illustrate this. How many people use deprotonated here? How many people deprotonated here? How many people use your enolate to attack here? How many people use your enolate to attack there? All that would happen. You're at home, just like go back, rewind and delete. Try this. So that's the enolated step one. LDA. No proton on this side. Two on that side. We get E and Z enolates, but I'm going to draw it as a negative. Then we introduce the electrophile. So draw what you get from the reaction of those two things. All right, so we have a nucleophile, we have an electrophile. Again, over there, the nucleophile is going to add in, the enolate will add into the carbonyl. We'll kick methoxide out. Methoxide will take the proton. The product of step two be that. Right, and you'll have methanol. Right, so again, enolate carbon attacks. How are your carbons, man? So that's the first intermediate. O minus takes out methoxide. Yep. So that, you get that? You're not done with step 2 yet, though. This is actually our final product. This is what we're going for. But what forms first in there, into step 2, is that. That's what we have to do. Don't know why we're here. Maybe it's close to 2, yeah.
Would those be an equilibrium?
Well, so this is an equilibrium and it's a pretty, it's roughly 50-50. This one, yeah, this is an equilibrium, but it is,
Isn't it enolate favored?
this enolate is favored.
Okay.
Yeah, heavily over, like methanol. So again, pKa of like 9, pKa of 16. And then step 3, add acid. That's the product at the end of step 3. So this is what, and we're gonna finish with this. We were kind of talking about this at the end of that reaction over there. The product you want over here, right? The neutral product that will actually isolate, chromatograph, do whatever we're gonna do next. You actually form that during step 2. And I promise, if you can look at old exams where this is a mechanism question, many students just go like, well, that's my product, so I must be done. But you're here with the methoxide grabs this proton, and the equilibrium, like every equilibrium up to this point is like 50-50 or favors starting material. What drives the reaction to completion is this last step being very favorable toward the enolate of the dicarbonyl compound. Right. Once you have that, now you can just add some protons in there, right? We'll protonate the methoxide, any methoxide that's floating around that we'll protonate that. Any LDA that was left, we'll protonate that thing, we'll get our product. All right. So on Wednesday, you guys need to turn in your acid-base worksheet. I'm gonna get some problems assigned for chapter 21 today. It'll be most of them at this point. I've kind of not wanted to give suggested problems. You guys are coming off exam 2. You had 2 other assignments for me, but it's time to get back into working book problems. If you have a hard copy that you brought, because I'm probably going to need to edit the Canvas settings. Like I think it said to stop letting you turn it in at 12:45. I can edit that, you can upload them, but if I have a hard copy, I can also do it. So turn those in, otherwise, see you, we're done. Okay, all right. Did it take it?
Yes.
Okay, all right. Okay, good, yeah. I will ignore it if it says it's late.